All right, everyone. Friday. See, this time I looked up the calendar. I know today is Friday. It's actually still snow outside. This is 2 weeks in the past. So last Wednesday, we finished up all our discussion on flat potentials. And everything up to this point has been nothing but e to the ikx, e to the minus ikx. I hope that you're just absolutely sick of it. And so we're going to finally get away from flat potentials. Right, no more free wave, no more step barrier, this or that. Not that we spent too much time on that, but those were kind of hideously complicated, so complicated that for the most part I just gave handouts, which you may or may not have looked at. It's okay if you didn't look at them. You don't need to, especially that finite barrier one, the one from last lecture. That handout is like 4 pages of algebra. That's hideous. I don't expect you to look at that. But we're going to finish up on that today. We're not going to have any more flat potentials. We're going to start on what's called, all right, so at this point, you're used to this now. Everything has a name, right? What's this problem's name? This is the Harmonic Oscillator, which is kind of a silly thing because what I mean are bonds. So we're doing chemical bonds. So that's the name. The name of the problem is Harmonic Oscillator, but really what it is, we're doing the quantum mechanics of chemical bonds. We're going to spend about a day and a half on this, and we're also going to get more, this is going to be more representative of what we're going to do from here on out up until the end of April, which is the end of the semester, which is that we're going to set it up, but the answers, because all of these are differential equations, it turns out in 18th century is when mathematicians figured out about calculus and differential equations. So they just started solving whatever. They would just make things up and solve it. Of course, we know the solutions as wave functions. And it didn't mean anything to them. But all of our answers are in 18th century textbooks. So we're going to set up the problem. We're going to look at an 18th century math textbook and get the answer, and then we're going to examine the answer for all these different kinds of properties and weird phenomenon. We're going to see something that kind of looks like tunneling. Remember we talked about tunneling last time. And so vibrational quantum mechanics, you see an aspect that's kind of like that. I've also got a little video. I don't think I'm going to show it today. I spent a bunch of time, I complained about that last time, how I spent 3 days making some quantum mechanical videos. And I've got one for bonds, but I'm going to have to show that next time because I won't quite get to it today. Okay, anyway, I've been blabbering. Let's make it definitive. Let's talk about CH bonds because those are kind of important. And I better draw some R groups. And those R groups could be H. They could be H themselves and whatnot. But CH bonds are obviously really important. And of course they would have some kind of equilibrium distance. Let's call that x naught. We're still one-dimensional. We're just going to call that vector. We're going to treat that bond like a vector, this direction. So we take the molecule and we'll line it up in the x direction. And CH bonds, I believe, are a little over an angstrom. I want to say like 1.2 angstroms. That's like fairly common. I think that's right. I'm not too sure. Anyway, all right, now what I'm going to do is I'm going to treat them like a spring. And that's pretty good. Now, you don't quite do that in PChem Lab. Next lecture, I'll tell you a little bit more about how you interface this with PChem Lab, but I'll do that next lecture. What you do differently in PChem Lab is that you use a different potential. Let's start with the harmonic potential, and then I'll tell you more about the PChem Lab potential next class. Anyway, so the potential we use is a spring potential, which is that force is minus a, okay, this is not a wave vector. This is the spring constant. So we say that there is a linear restoring force whenever we pull the bond, pull the spring, or compress it. Compression happens, and the force is proportional to how far you pull the spring. Okay, so that's easy. Now a little bit of classical this and that physics from your physics class, which hopefully you took as a freshman, that force is equal to the derivative of minus the potential. And the minus is because otherwise that sets the direction correctly. That's why PDD or something, some of your equations from PChem 1 work the way they do because of that minus sign. Work was PDD, remember that? Okay, anyway, so what do you do with this? All right, so let's plug in KF. I just got rid of the minus signs. And you notice we're solving a differential equation, and we did a little bit of that in the extra hour, so I'm going to bring that partial. It always kind of disturbs me that you can just move partials around like that, but you can. Okay, and of course, to deal with this, I need to integrate it. And if I integrate this thing, what you're going to have is 1/2 spring constant. And so that is the potential that we plug into the Schrodinger equation, where x now becomes an operator. Now remember that probably sounds like, well, wait a minute, then how is it different? The answer is it's not. The way that operators are different than just calculus, this or that, how is x operator different than x? There usually is no difference. Occasionally you run into some differences, but it's actually kind of rare. X is just x. X naught, of course, is a constant, as I just mentioned. I think it's 1.2 angstroms for a CH bond. Okay, so what do you do with this sucker? Schrodinger equation. All right, 1h minus h bar squared over 2m. Remember that it's always the kinetic energy operator that really messes things up because it's a double. This is the differential part. This is why it's a second order differential. If it wasn't for that, everything would be way easier. And okay, I've got double derivative, wave function, and of course that's the solution. And spring constant. And here, you know what? I need to write all this out. But I can tell you that this x minus x naught, that's actually going to be a bit of a problem. It's just going to make this way, way, way more complicated than it needs to be. Here's a solution. Check this out. What I'm going to do is I'm going to transform this picture, right? So again, it's a harmonic potential, right? It's just a parabola. It's not a very good parabola. It bothers me, it has to be perfect. A parabola where the bond is centered at x naught, again 1.2 angstroms. Now what that means is that if the wave function just wants to wander to the right, that means the bond gets longer. It means that the CH bond can be shorter, and that's to the left. Okay, that's all fairly simple to interpret. Here's what I'm going to do instead. I'm going to center it about 0. Okay, so what that does is it allows me to do this. And that is a lot easier to write. All you have to do is change your interpretation. So what that means is that to the right of 0, that represents the bond expanding, and to the left of 0, that means it's contracting about its equilibrium. Now, one thing I sometimes throw, like explain what's wrong question on the exam, I will say, okay, this parabolic graph for a bond, what does x equals 0 mean? And some people say, well, that means the bond length is 0. Okay, all right, now that would mean that the C and the H are overlapping in space. The two atoms are overlapping. So, no, just think about, if you don't remember that, just think about what that means, okay? X of naught means that the C and the H are at their equilibrium bond length of about 1.2 angstroms. That's what that means. Again, I'm doing that. It's not really much of an approximation in terms of like how to think about it. It's actually kind of more sensible to think about it this way. X of 0 means that everything is exactly what it should be. That kind of resonates, right? That makes sense. And it sure as heck makes the equation simpler to solve. Not that we're going to actually solve it. I've seen this thing solved before, and it's a real, it's about a day, a little over a day of, no, it's about 1 day. 1 day of a bunch of calculus. Okay, so here's the Schrodinger equation, and what I've done is I have the potential energy there, the harmonic potential with our reinterpretation right here. And what's kind of neat is now, remember, up until now, that's just either there's been nothing here, 0, or just a constant. And that was stupid because it just simply shaved off some energy. Okay, then there were different regions. Anyway, yeah, so it got a little complicated at times. But there you go. So this is our Schrodinger equation for a bond. And now we actually have a potential surface that has some structure. Okay, here's the deal. As I just mentioned, to solve this, it takes most of the lecture. And it's just a bunch of pretty, difficult math. Let's drop that. I kind of did some of that anyway with even with like the finite barrier and finite box. I just said, oh, look at this handout. So just like then, I don't actually have a handout on this. Let's just drop it. Not worry about the math. Let's just look at the solution. Now, of course, remember, the solution is the wave function. Right, that's what I mean by solution. We then plug the solution back into the Schrodinger equation to start figuring out new things, like what's the energy. So remember, there's kind of like an order to these things. Regardless, the solution is a wave function, and again, it's been solved long before even quantum mechanics exist. All right, so what does it look like? Okay, so what we have to do is define a constant, because this has already a whole mess of constants. We got h bar, we got a mass. Really, that ought to be a reduced mass, but it's a detail. I don't want to like test you or get caught up in a bunch of details, but regardless, okay. So if I define alpha that way, the wave function looks like this. Okay, there's parts to it. There's a normalizer. There's this thing, and I'll explain what this is. It's called a Hermit Polynomial. And then we've got a bell curve. Remember, e to the minus x squared is a bell curve. And of course, it has to have some width. The thing you divide it by is the width. That's 2 alpha squared. X squared is divided by 2 alpha squared. So I hope my alpha isn't too awful to look at. It's bothering me. Hold on, let me try to write that alpha a little bit better. There we go. I hope that's a little better. So 2 alpha squared. The 2 is not squared. If it was, I would write 4. It's 2 alpha alpha, okay, in the denominator. All right, anyway, just want to make sure you get that. Okay, now, the various parts are, of course, that is the normalizer. So when the function is squared, which I don't see any imaginary, I don't see letter I in there, it's not imaginary. So I can just take this whole thing and square it, and then I would integrate it from minus infinity to infinity, and the normalizer will make it equal 1. Okay, so again, we've been talking about normalization for an incredibly long time. Okay, this is called the Hermit. Don't worry about memorizing. You're not going to see this again. But I'm going to tell you what it is. Hermit Polynomial. Okay. Now, what that does, that is what gives it extra energy. So it actually gives it nodes. So tell you what, let me go ahead and draw some of the states. And that will give you an idea what the Hermit Polynomial does. Okay, I can tell you that the Hermit Polynomial is 1 in the ground state, and the normalizer is a constant, so I've just got a bell curve. E to the minus x squared is a bell curve. So here is the ground state. Right, kind of looks familiar. We've seen a bunch of bell curves, right? Okay, now, to this end, now let me explain what this little, I think this is mu. Mu is, I sound French, don't I? This is our quantum number. That is our quantum number, and it goes from 0, 1, 2, ... Okay. Now remember that quantum number, you've seen them before. That was n sub x, when we did the particle in the box. It was related to the number of nodes. So you may recall that I hope you just straight up remember that that we had an n sub x in our wave function for the particle in the box. It also showed up in the energy. The energy was proportional to n sub x squared. Oh, excuse me. I'll edit that out. I've actually already had COVID, by the way. I got it in the supermarket according to my doctor, so I'm not sick. Anyway, okay, so, oh my God, what was I talking about? All right, I was talking about the quantum number and how you had seen a quantum number for the particle in a box. So, remember that in the particle in the box, there were multiple solutions. I mean, they actually kind of look like this, right? And the quantum number, n sub x, kept track of them. It told us, because it was part of the energy, it told us what the ground state was, it told us what the excited states were. The quantum number here has the exact same purpose. Nu, 0 is the ground state, and 1, 2, 3, blah, 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 are excited states and higher and higher and higher excited states. Okay. Now, the reason I was going off on that is because I had to describe the next wave function here and what the Hermit Polynomial does. So the bell curve is the ground state. So here's the first excited state, and what the Hermit Polynomial does, it puts a node in it. So there you go. I think you probably could have guessed what that looked like without me drawing it, right? And then the next state has two nodes and whatnot. So again, this is the quantum number. It, just like the particle in the box, it kind of looks like a particle in the box, right? It tells you the number of nodes. It keeps track of what is what. For 0, ground state, 1, first excited state, 2, second excited state. So hopefully that's obvious. And it also tells you what the energy is. Obviously, by definition, the ground state is the lowest energy. First excited state's next. Second excited state is higher energy, on and on and on. All right, so that's kind of silly. Okay. Hermit polynomial and normalizer. Normalizer I won't talk about because the lesson learned here, I'm going to show the Hermit polynomial, which is, I'm going to show you what a recursion is. A recursion relationship means that what I do is I tell you, like, I've already told you the Hermit polynomial for the ground state is just the number 1. What a recursion relationship does is it takes that information and allows you to generate the Hermit polynomial for the subsequent excited states. Now, this, I don't know, that maybe I'll put this on the exam because I would consider it an easy question. It's just a matter of can you follow mathematical formulas? I often don't put it on exams because I don't want to test whether you can follow mathematical formulas, but sometimes, maybe I should, because again, I've been saying for, ever since this class began, that your math ability is, developing your math ability is very good for you. The better you are at math, the better worker you are, you're more hireable, right? So with that said, I'm going to show you this, and I'll let you know how I'm feeling when I write the second exam, whether I put something like this on the exam. Anyway, okay, so here's how it works. So let's make a table and for the ground state, and I'm going to write down the Hermit polynomial, and I've already told you that it's 1 for the ground state, and here is the recursion relationship. Okay, so notice I am talking about, for the next state, when I say nu plus, oh, that doesn't look so good. Nu plus 1, so that's for the next state. That's equal to 2x over that alpha. And again, I hope you're not having too hard a time with my alphas. Okay, the previous state. Anyway, it's just a formula. And so let's apply it. All right, so this is what you have to be good. By the way, if you're curious where this comes from, it comes from the solution. If you see how people solve the second order differential equation of the Schrodinger equation, this one, the harmonic oscillator problem, is one that is solved using the Schrodinger equation. Now remember, up till now, we've always just looked at the particle in the box and just figured it out. Oh, it's just sine pi x. For the finite box, oh, it's smooth and continuous at the boundaries. We always had externalities to figure out the wave functions, even if we just kind of just said, oh, it's just sine pi x. The harmonic oscillator is actually solved using the Schrodinger equation, using advanced mathematical Diffie-Q. When you actually apply that ability, if you're a math major, of course, then this comes out of the solution. So that's where it comes from. Anyway, for our purposes, it's given. All right, but now we got to use it. Okay, notice that obviously the first excited state, we got to do the first excited state next. So let's do that. Okay, that means I'm looking at, this is the trick. I swear to God, this will get you. This is why I might put it on the test. You are looking for, right, the Hermit Polynomial for nu of 1. Okay, but according to this formula, sorry, you're looking for this. Therefore, in your formula, nu is 0, right? So again, this is odd. I mean, it's so simple that you can get yourself way confused. You know how that happens sometimes. If I'm looking for h1, right, then because I've got nu plus 1, nu is 0. Right? It's really elementary, but I swear to God, it has a way of just screwing you up completely. Okay, so 2x over alpha is just 2x over alpha. You don't have to think about it. And now I've got 8. Now you see how this comes about? See why it matters? Now I've got Hermit of the ground state, h0. And I know what that is. That's h0 is 1. Okay. Minus 2 times, again, nu is 0 times actually something that doesn't exist. I don't have an h minus 1 that's up here. It doesn't exist. But that's okay because it's multiplied by 0. Doesn't matter. So this is 2x over alpha. Okay, so we put that into our... There we go. Now we put it in the table. So now you see how the game works. Let's do one more to make sure you get it. Okay, now I've got to do the next excited state, the second excited state. And therefore, nu is equal to 1. Okay, so 2x over alpha h1, which is 2x over alpha. So it's the square it, right? Minus 2 times 1 times h0, and that's just 2. I can just, I hope you don't mind if I just do that, right? It's obvious, okay. 4x squared over alpha squared minus 2. Is that right? Let me check my notes. Yeah, so 4x squared minus 2 over alpha squared. Okay, so that doesn't look good. There we go. Yeah, that looks better. There we go. Okay, so there you go. Now I know it's a little silly, but I did want you to see how that worked, just because. And let's see. So let me make sure that you get. Let's keep this up here. Let me make sure that you get a feel for how the wave functions look now that we have this information. And it's kind of important for reasons that are going to come up in a second. So remember that the ground state is, of course, just a bell curve. It's an awful looking bell curve, isn't it? Anyway. Okay, so that's just a bell curve. And let's also recall what it means is, what you're seeing is some probability. What you're seeing is that the wave function, remember, the wave function is squared, but it doesn't look that different. It says that there's some probability for the bond to be to the left and right at 0. For the most part, the wave function is peaked at x equals 0, but there's some probability to be to the left and to the right of 0. Now, not forgetting what that means, what x means. X is the displacement from equilibrium, right? Remember I already told you that. I asked people, what does X of 0 mean? And some people say, oh, that means that the bond length is 0. And so what does to the left mean? That you have a negative bond length? What is a negative bond length? No, this means that you are likely at the equilibrium bond length, but you could expand or you could contract. So I know we think of springs as being collapsed and you only pull on them, but think of this as like a spring that's like, maybe it's like been bent, you know, it's been a little bent out of shape so it can compress or expand. So that's how we model this. All right, now, again, that's our interpretation, but now let's look at the Hermit polynomial. It's, whatever, some constants, 2 divided by alpha, who cares? It's an x. Okay, now I can draw an x, it looks like that. And now, I want you to try this in your head. You can do this, multiply the 2. Multiply the 2, right? And let's see, what would happen? Well, the bell curve is going to turn, the bell curve is going to turn negative. 0 times anything is 0, and then it'll turn positive, right? So you kind of, you just kind of mess up the bell curve, right? There you go. I don't know why I did that little tick mark like that. Anyway, so there you go. That's, I know actually, it looks like I flipped it over earlier. Sorry about that. But anyway, so this is what the first excited state looks like. And then we can do the second excited state and on and on and on. But I think you get the idea. Just take your bell curve and multiply this. You can see it will get a little bit more complicated, but this gives you the idea across. Now, what I really want you to get from here is that you have some symmetry, like the ground state is symmetric, it is like even symmetry. The first excited state is odd symmetry. The next state would be even symmetry because x squared is even, then it would be odd. You want to just think in those terms, and I'll show you why in a minute. Tell you what, let's do a couple more problems. Let's do average position, and then we're going to do the energy. And I think that'll be enough for today. I need to wipe out the board, so give me a few moments. I'll be right back. All right, we're back. Okay, so remember, the name of the game is now we have our wave functions. What can we do with them? So let's do average position. Why not? I think my pen is dying, so anyway. All right, average position. And we're going to use expectation value. Remember that. You can't really do position with eigenvalue. That's not going to happen. You have to do it with expectation value. And as I mentioned, if anything on the test or homework, I'll make sure you know what the limits are. Particle in the box, because of the high potentials, left of 0 and right of L, the limits are 0 to L. In this case, it's minus infinity to infinity, which is what you more normally run into that one. Okay, so then we write the complex conjugate of our wave function. I'm going to just call the normalizer n. Trust me, that's going to work just fine. And tell you what. Now, before I do that, hold on a second. Let me think about what I want to do here. I just realized something. Remember I was telling you about even and odd wave functions? Okay, so let's do that one. That's the ground state. That one's gonna. Why would we bother to do that? The average position on the ground state, that's going to be 0, right? I mean, I hope we didn't have. Let's not even do that. No, it's going to be 0. Look at it. It's even, right? It's even. So of course. On average, it's in the middle, and by definition, the middle is at 0. Okay, now let's instead, tell you what, and of course, the even ones will be like that. So let's do an odd one, right? So let's do the first excited state. First excited state. So what is the average position for the first excited state? Clearly, it's going to be like a better problem than the ground state. Maybe I'll put that on a homework or a test. And again, you should be able, I tend to do that. I tend to sometimes ask a little bit more complicated. Like this looks kind of complicated, right? But you should know the answer. You should know it comes out to be 0. So anyway, I will do, just to do a harder one, I will do the first excited state instead. So the normalization, as you're going to see, by the way, normalization, I'm just going to leave it like that because I can do this problem without knowing it. Now, I happen to know that ahead of time, and you don't know that a priori without me telling you, and I'm aware of that, so don't worry. I'm not going to have you do some kind of question that requires specialized knowledge. Here, I have to give myself some room. Oops. Let's see. Oh, this is a lot to write out. I ought to speed up time or something. Okay, normalization. Now remember, this is the complex conjugate, but there's no letter I in it, so there's not much to do. Over alpha. I hope that's the Hermit Polynomial. Okay, one of the things that causes people problems is that you see you have to multiply this times that. And I've seen people really mess that up, which is bad because I give you identities. Okay, and yeah, I give you identities. Clearly, we're going to have to simplify this. So let's just do that. Really isn't much to it. It's just an algebra problem, and hopefully, algebra problems, that's great because algebra problems should be relatively easy. Okay, n squared 4 x squared alpha squared. I'm looking at where all the constants are and just kind of gathering them up in my head. Okay, then I've got xx, well, not x squared, x cubed. Ooh, gotta be careful. X. Now remember, the operator x is just an x, right? Okay, now again, look out for this. E to the blah, blah, blah comes up all the freaking time, right? You got to be able to multiply this times that. And I've seen people just really screw this up. When you multiply two exponentials, you take their argument, that's the to the blah part, the blah is the argument, and you add them together. In this case, as with wave functions, they're usually the same thing, so you just double the argument. Okay, so that means I've got minus x squared, 2x squared over 2 alpha, so that's just x squared over alpha, alpha squared, anyway. Okay, there we go. If I put the limit, you have to put the limit. Okay, so now, of course, if on an exam, you would look at the identity, and I would have the identity, you get the right answer, but, you should have had this in your calc class. So I hope that this sounds familiar. I hope that you've heard this before. What I'm saying is let's see here. Constants don't really matter. That's odd. X cubed is odd. And a bell is even. Do you remember this? When you integrate an odd function, and odd times even is odd, the answer is 0. Or, look at an identity, and I won't even write it down, it's just 0. This is 0. Either you can look at an identity, and the identity says this is 0, or you recognize that you've got an odd and even function integrated from infinity, minus infinity to infinity. And hopefully you had in your calc class, that's 0. In either case, it's 0. Now, the lesson here is, in case you already forgot, because it doesn't help that I accidentally erase the graph, that the wave function, here, I got it. Now, what's funky about is that, remember, we're doing the first excited state. This is so weird. This is so weird to me. The wave function has a node at x equals 0. Now, remember, that's the equilibrium distance. Now, since the square of this is the probability, and that actually doesn't really matter so much, it says that in the first excited state, that the bond is never at its equilibrium point. It's always either too far or too close, but it's never there. The probability of being at your equilibrium point is 0. But on average, you're at your equilibrium point. What? Right? Now the answer is there's no weird mystery that a fish runs up the stream and turns into God or something like that. It's it is true that the bond is never at its equilibrium point, but it's just as likely to be compressed as much as it is expanded. Sorry. It's just as probable to be expanded by yay amount as it is to be compressed by yay amount as it is to be expanded by yay amount. Okay, well those negative and positive yays add to 0. So, and another thing is that also just look at the wave function. It's again symmetric. So on average, it's in the center, despite the fact that it's never in the center. On average, it's in the center, although it's never actually in the center. I mean, that's, again, this is why we have a class called quantum mechanics, because you run into crap like that. I shouldn't call it. Anyway, all right, moving on. Let's see. What have I got? It turns out, okay, there's one little factoid. A little fact about this. It turns out that the expectation value for any wave function, for ground state, first excited state, second excited state, third excited state, the expectation value of the ground state, first excited state are 0. We just proved that. But for any excited state, second, third, fourth, fifth, all these wave functions on average are at their equilibrium point. And that's because, again, the way the parabola works is that you may be a little expanded, but you're equally likely to be compressed just as much. So it doesn't matter what excited state you're in, the average position is always 0. And that always comes down to a fact that you're going to have an odd times an even function in every time. Every state that you can plug in times x is going to end up being odd times even, which is odd, and it will integrate to 0. Okay, just wanted to point that out. All right, now, last bit we're going to do is we're going to do an energy calculation, and I won't do that by expectation value. I won't do that by expectation value because that's kind of painful. But I did it in this case because I had to. I'm going to use eigenvalue way to do the energy. And we're going to do the energy of the, what am I doing? Better check my notes. I'm going to do the, God, what am I doing? I'm doing ground state, aren't I? Yeah, I'm doing ground state. God, I'm sorry. Look at my own notes. I'm doing ground state. I'm going to get a new pen. It's been dying. And I will only do this for the ground state, and I'm going to use the eigenvalue way because this is just a little bit easier. All right, and so what am I going to do here? Okay, so this is going to take a little. This is kind of a lot. Okay, so I've got like my whole page worked out on this. So you want now. I hope you should be writing notes too, right? Because that's how you learn this stuff. You're not watching Nova, okay? Right? This is not television. So hopefully you're writing your notes. So you need about a whole page for this one. And remember that we're going to be doing a lot of these whole page type of expectation values or eigenvalues. Our wave functions are going to get more and more complicated. So more and more we're getting back to those Maxwell-Boltzmann equations go across the board. So just heads up on that. Okay, now, new pen is always a little bit like this. In a few moments it'll be in good shape. This isn't too hard to see. Maybe I'll up the contrast on the video. Okay, kinetic energy operator. Now the thing about the normalization constant, it never matters in an expectation value, in an eigenvalue equation. Yeah, that's not going to work, is it? Yeah, I can barely read that. Let's just limp along with this last pen. What's weird is that I just have to like write with it once, and like in an hour it'll be good. Anyway, yeah, that's okay. It's about the same, isn't it? Okay, so there's the wave function. Now remember, again, when it comes, the reason I want to do this with the eigenvalue way is because I don't really need to worry about the normalization. I just need to associate the normalization with the wave function at the end. And if you don't know what I'm saying, if that doesn't make sense to you, you'll see it when I get to the end. I just got to be careful about my 2's and my alphas because I know they look the same. Okay. And at the end of the day, what I need to do is find some constants times n e to the yada, yada, yada. Okay, next thing to notice. I've got my kinetic energy and I've got my potential energy. Now the question is, what do you do with this? Oh, no one's in here, sorry. Nothing. X is an operator, but it's a dumb operator. It doesn't do anything. Now recall that we're going to have to get to a number times the wave function. So again, this is what I mean about the n, how you have to associate n with the wave function, because you've got to just factor the wave function away, and you should have a bunch of constants, that's the energy. Now notice how these play off against each other. Potential energy, there's nothing I can do with an x. You know, there's no derivative, it's just here. But this is a problem because x times the wave function is not a number times the wave function, right? This does not work in the eigenvalue way. Here's what's going to happen. The kinetic energy operator is going to kill the potential energy term, right? You see that? This thing is going to spit out energy times the wave function, but it's also going to have minus that. So the kinetic energy operator destroys the potential energy operator. It has to, because you can't do anything with that x squared. And again, there's leftover, which will be that. This is how they'll always work. You know, this is a way I want you to be aware of that, because you're going to be conscientious of what you're doing when you're doing these types of derivations. Okay. Now, also, we're going to run into a product rule, and that's how this is going to get split into two terms, one that kills that off and one that gives us that. So there's a method to this stuff. Okay, I need to hurry. I see I'm almost out of time. And yeah, that mass should be a reduced mass. I hope you remember that about springs, but I'm not going to worry about that so much. Okay, first derivative of this thing, and I hope you know that the exponential always survives. And then you multiply the exponential times the derivative of the argument. So that's minus 2x over 2 alpha squared. So that's x over alpha squared. Don't get confused with thinking that that's a subtraction. That's minus x, not negative x, not minus x. Again, the exponential survives. And let me just do that, because in other words, my arm kind of hurts. Anyway. What's in brackets? In brackets, there's nothing else. And there we go. Okay, next step. All right, so now this is going to get kind of nasty. You see, I told you a product rule. See, now I got a product rule. I got an x, e to some stuff. Okay, so what am I going to do with that? Here, I'm going to take out the n, because otherwise I'm going to get confused. Let me make that look nice. There we go. Okay, all right, I have to think about this. Okay, I will do the derivative of the x, which is nothing, minus e to the, I'm sorry, derivative of x is 1, sorry, minus x is just minus 1. Don't forget the alpha squared. Okay, now I can see that this guy is going to actually turn into this. I can see that. All right, now I've got my product rule bit. And I'm going to leave that one times the derivative of that. Now I can tell that that's going to kill this off, right? Well, here, let me just do it and we'll see. Okay. Now that's going to be minus, so I've got, it's definitely going to turn to a plus. I'm just going to go ahead and do that. Alpha squared. Derivative of the inside, which is minus x over alpha squared. Let me check my notes because I am. Yeah, x over alpha squared. Okay, you see I've got an x squared. You see I've got an x squared going on here. Either minus x squared over 2 alpha squared. Plus, let me go ahead and, I know I was lazy before. And again, I want to point out that all of this actually kind of makes sense. I know you can get lost in the algebra, but in bracket because of the normalization constant here. All right, now you can see here that, what have I got? I have got, minus, no, this has got to be minus, right? Have I made a mistake? I feel like I've made a mistake. Let's see here. Okay. Yeah, it's okay. It's okay. Plus, minus, right, okay. Okay, so let me show you what got me confused. X minus x is plus x squared, and I've got to kill off that plus x squared, but my other minus is there. Okay, anyway, I'm babbling like an idiot. Let me do the last step. I need to note that alpha squared is h bar over m spring constant to the half, and therefore alpha to the fourth power, because I've got an alpha to the fourth power right there. So you see I have an alpha squared and I have an alpha to the fourth power there. And so that's just h bar squared over. Okay. So what does that give me? That is going to give me h bar squared, this term, the minuses cancel. Then I've got mass from here. I've got 1 over alpha squared, so I'm going to invert that. 1/2. Okay, now I need to, so I've taken care of all the constants, so now I need to associate the normalization with the function. Okay. Now again, I want to point out that this term ends up being my energy. Here's the wave function, and that means that this has to be the energy right here. And we'll work a little bit more on this in a second. Now this term has to cancel out that term. Now let's see that it does. Okay, minus, minus, minus is minus. Okay, so I've got a minus h bar squared over 2m times mkf over h bar squared is going to be in 1/2 from the 2m there. 1/2 minus 1/2 kf from right there. M cancels that m. X squared. N comes from here. And our exponential is still there. Okay, minus 1/2 kf x squared wave function plus 1/2 from the original potential energy term plus 1/2 kf e to the minus x squared over 2 alpha squared. There you go. We're basically done. I can see that I'm out of time. God, I'm sorry I used the board so terribly. But let's see here. That term wiped out that term. And so what are we left with? Here, I never used this lower board, but I finally had a reason to. Okay, we are left with energy is h bar, h bar squared over 2m, m kf over h bar squared to the half, which ends up being, let's see here, let's see, I've got h bar, those cancel. I've got square root of k over m. Is that right? Yeah. one h bar over 2. Okay, there we go. Now, you may recognize this deal as actually that is the angular frequency. And so this is, let me put it in the term that you probably have seen. 1/2 h bar frequency. There you go. All right. Now, again, I know I'm out of time, but here's what you can do. You then do this for the other excited states, do 100 of them, have a computer do it. And what you find is that you can express the energy as a function of the quantum number, and it's always this. It is the quantum number plus 1/2 h times the frequency, every time. Okay. I'm sure that there's some fancy mathematical way to prove that in absolute sense, but there you go. Okay, God, sorry that this was kind of bloody awful, but you got to get used to this. This is going to happen again, really about 5 or 6 more times. So the trick is just be really freaking careful. And remember, and I know you're sick of me saying this, but I just can't emphasize it enough. If you can be careful with this kind of stuff and get answers, you're a rare person with good skills that's worth a lot of money. So when you're writing this out and you're getting sloppy and you're like, I don't care about this, then that's fine, I get that, but you also don't care about money because those kind of go hand in hand. So think about that. All right, next time we're going to do a couple more tricks with the harmonic oscillator, and then we're going to start getting into multi-dimensional quantum. It'll be actually kind of an easier lecture. This was one of the harder lectures. The next ones will be a little bit easier. Okay, and that today is, I forgot, today's Friday, I already forgot. So I will see you all on Monday.